For a particle in circular motion around some center of rotation c, the angular momentum of the particle is defined as the product of the particle's mass, the particle's instantaneous velocity v, and the particle's distance from the center of rotation r. mvr. This is angular momentum. If you divided me and the chair and the books I'm holding into a bunch of tiny little particles and found the MVRs for every one of those particles and summed them all up, you would have the angular momentum of the entire system of me, the chair, and the books. But notice that this is just a mathematical expression combining three different measures. It's not a physical substance you could pull out of a particle and hold in your hand or put in a jar and study. It's kind of like, taking my weight and multiplying it by the number of countries on Earth and then multiplying it by the time. However, unlike something like that, this concept is really useful because we have found that in our universe, over time, it is conserved. If the particle is pulled towards the center of rotation, its R value will go down. But angular momentum is conserved, so one of these other variables must go up. Well, at low speeds, mass is essentially constant, so the only option is for the velocity of the particle to increase, for the particle to spin around faster than it was before. If the R value gets smaller, the velocity must get larger, or else a law has been broken.